A general theme that will be recurring in almost every single lecture in this course is that we will see individual behaviors, often driven by self-interest, aggregate into a state across all the users, a global configuration in a social, economic, or technological networks. And sometimes it can aggregate into a fair and efficient configuration. We'll try to quantify efficiency and fairness in the course. And such a phenomenon of local behavior aggregating into a global configuration that is desirable is going to be helped by some kind of feedback signals, which could be, say, a pricing signal, or maybe a congestion signal, or maybe a collision signal. Some of these feedback are explicit. Okay. Some network element tells you a specific action that you need to take. Sometimes they are implicit. You measure something, for example, the current SIR at time t, and then use that implicit feedback to adjust your own individual behavior in the next iteration. Now we're going to understand the specific behavior in distributed power control from two angles now. And in that sense, we're using DPC as a way also to introduce us to the terminology and the basic notions in two powerful mathematical modeling languages. One is the language for constrained decision making called optimization theory, and the other is the language for strategic thinking by intelligent agent called game theory. Now let's start with optimization theory. This is a word that we use in our daily language. Right? We try to optimize something. We try to optimize our time, our holiday schedule, our work schedule. And if you think about it, in an optimization, you have some degree of freedom, which we will mathematically call optimization variables. You have some objectives you want to maximize or minimize. For example, maximize your employability, okay, your happiness, minimize the cost it takes to finish some task. And then you have some constraints. Without constraints, the problem would be too good to be true. This could be constraints on the time you have, on the money you have, on the energy you have. For example, when you look at your schedule this weekend, you may say, well, I can pick my variable to be spend the time taking a course like this one, or spend the time to watch a movie. And the objective function may be, well, make me as happy as possible. And the constraints, say, is you only have 24 hours in each day. Now we will see a mathematically precise, unambiguous language called optimization theory. And in each optimization problem, there are four main data fields. One is, of course, the objective. Now, in the case of transmit power control in cellular networks, the objective is to minimize the sum of the individual transmit powers. So we'll write minimize the sum of the pi's over i's. So this is a power minimal configuration, subject to the constraints that you have to achieve the target SIRs for all the users. The SIRs for each user indexed by I must be no smaller than the target gamma I. And you need this to be held not just for a single I, but for all I's. And then you need to vary the degree of freedom. In this case, obviously, it is the set of transmit powers. And everything else are constants, including the channel condition, the GIJs, the noises, NI for each receiver, and the target SIRs, gamma. Towards the end of this lecture, we'll also see what would happen if these target SIR values become variables as well. But for now, they are held constant. Now, once you have an objective function, a set of constraints, and you know what is variable and what is constant, then you have an optimization problem. Pictorially, what we are looking at in this case of transmit power control is visualizable in the following cartoon. Now, suppose we have just two users, so we can draw in a two-dimensional plane on a piece of paper, slide. And the first user, SIR, is on the x-axis, the second on the y-axis. And we have a region. Okay, it's a shaded region here that denotes the set of feasible SIR values. Okay. Now, ideally, you want SIR for both users to be high. But as you know, because of interference, that is not possible. So let's just look at those SIR1, SIR2 values that are possible. And we call these the feasible SIR values. So any point inside this region, okay, is a feasible point. But there are also inferior points because I could find a way to increase SIR for both users. Okay? So any points in this region would be strictly better than this point. At the same time, every point outside the boundary is infeasible. Now, what about the points exactly on the boundaries? We call those points Pareto optimal. Now, clearly, there are infinite number of these points on the boundary, and they are all Pareto optimal. In some sense, they are not directly comparable. Okay? Points inside are feasible but inferior. Points outside are infeasible, so don't even worry about those. Our job is to find a point that's at least on the Pareto optimal boundary. That means you cannot increase one dimension without hurting the other dimension. Those points formulate or form the boundary of this region. Now, which point to pick then? That would depend on the objective function. You have to impose some other objective function in order to pick exactly the point that you like most. Now, later we will see this theme of trade-off. Okay? Trade-off in this case between two users, SIR, and in general, the trade-off between any competing users in a social, economic, or technological networks. And we'll always want to operate on the Pareto optimal boundary. At least pick a point that is Pareto optimal. You cannot make one user happier without making another user less happy. Symbolically, in mathematical language, we say the optimization we have is to minimize the summation of the p's, let's say from the first to the nth user, they're all together n transceiver pairs, subject to the condition that the SIRs for each user, which is a function of the entire power vector p because of interference, must be greater than or equal to the target constant gamma I. And this holds true for the first, second, up to the n transceiver pairs. And the variable is clearly the p vector. Now, this is our first optimization problem. We will encounter at least 5 or 6 more throughout this course. Of course, this is actually a shorthand notation. Okay? If we write out the definition of SIR, okay, then what we have is Pi GII over summation across all j's not equal to I, Pj Gij plus Ni. And we want that to be greater than or equal to gamma I. If you look at this, say, gee, this is a pretty complicated expression, right? I got a numerator, I got a denominator, and sums in the denominator. But actually, it is an easy problem in disguise. What you can do is to put the denominator to the right-hand side, multiply by gamma, and then move the entire expression back to the left-hand side, subtracting it off. Then what you have is the following. Okay, Pi GII minus gamma times summation of j not equal to I, Pj Gij plus Ni, okay, greater than or equal to 0 for all the i's. What kind of function is this in our variable? Remember, g and n and gamma are constants. The only variable is p. Well, this is just some number multiply pi. This is just some number multiply pj, and this doesn't even depend on the p's. So this is actually an affine function, or we may say it's a linear function. So we are talking about minimizing a linear function, p1 plus p2 da 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 pn, subject to the constraint, which is also linear function in our variable p. When we minimize a linear function subject to linear constraints, we call that a linear programming problem. Now, this programming has nothing to do with computer programming codes. Okay? It refers to a mathematical program. So linear programming, this terminology that dates back to 1940s, refers to minimizing linear functions subject to linear constraints in your variable. Of course, if gamma is also a variable, then this is not a linear function in both gamma and p. But that's not our worry today. Our problem today is fix gamma, just vary the p's. And this is an LP. Now, LPs are easy to solve in theory and in practice. But as we will see in lecture 4, when we talk about Netflix price and recommender system, we'll see that the watershed between easy and hard optimization problem is actually not linearity, but so-called convexity. We'll come to that in later lecture. All right, so now we have defined what the optimization problem is, and we have recognized that it is a linear programming problem. How can we solve it? In fact, if you only need to solve this in a centralized computer, then there are many ways to solve this computationally efficient way. But if you want to solve it in the context of a cellular network with distributed action and no explicit message passing between the base station and the mobile station, then that's not easy. In the advanced material part of the lecture, or in section 1.4, advanced material section of chapter 1 in the textbook, we will see the proof of convergence of the DPC algorithm to an optimizer of this problem. In other words, the DPC algorithm is actually a distributed solution method to solve this specific linear programming problem in the physical context of wireless cellular network. Now, before we leave this module of the lecture video and move into the game theoretic interpretation, let's just quickly go through a general terminology for optimization problems. Now, we have seen that optimization problems have constraints. And we say that a variable picking certain numerical value gives you a feasible solution if it satisfies all the constraints at the same time. And if this problem has no feasible solution, then we say the optimization problem itself is infeasible. Now, second, there might be infinite number of feasible solutions, which is typically the case in the optimization problems for this course. And then we're going to pick out the best one according to some minimization or maximization criteria in the objective function. Now, if a particular solution, let's say a vector x with a star on top to denote that it is optimal, we call this vector an optimal solution if it is A, feasible, because otherwise it doesn't even satisfy all the constraints, and B, it is better, or more strictly speaking, no worse than any other feasible solutions. Now, what do you mean by no worse than? Depends on whether you're talking about minimization or maximization. For a minimization problem, it means that it is at least as small as any other feasible solution will give you in the objective function. So if you pick any other feasible x star, stick into the objective function, which is denoted as f in general, then f evaluated at this x star vector will be less than or equal to that. That's if you are minimizing an objective function. Of course, if you are trying to maximize a function, then bigger the better. Then we say x star evaluated at x star for this objective function will give you an value for the problem that is at least as big as any feasible x vector. This then we call optimal solution. As you can see, sometimes there's no optimal solution. Sometimes there's one, and sometimes there are many, in fact, infinite number of optimal solutions. Later, we'll also try to make a differentiation between globally optimal versus locally optimal. The definition we just talked about, comparison with any other feasible solutions, that is global optimality. If you say that this is no worse than any other feasible solution in a small neighborhood around this point, then we call that solution locally optimal solution. So these are the terminologies about feasible solution, globally optimal or locally optimal solution that we will be using again and again in the future lectures.